Stellar Nurseries.
Okay. Okay, hello. I'm Samantha Benincasa. I'm a postdoc at UC Davis, where I'm working. Microphone? It's good? Okay. It's just not sitting on my dress. So I'm working with Andrew Wetzel and Sarah Loebman. Now I'm a postdoc at UC Davis, and I'm going to talk to you today about the interaction between GMCs and star clusters in Latte. So this is a beautiful image of 30 Doradus, which is a star-forming region in the LMC. And what I want to convince you is that everyone should care about the interaction between star clusters and GMCs. So as the birthplace of stellar clusters, GMCs and their gas tell us a lot about the initial conditions for star formation. So the two are really intimately tied. And they tell us a lot about how star formation is regulated. So the GMC lifetime, which is specifically what I'm going to talk about, tells us a lot about the efficiency of star formation. And this is the small-scale type of efficiency that Florent was ranting about. And it tells us a lot, like I said, about how star formation is regulated. But star formation is a bit of a tricky beast to study in simulations. So young stellar clusters, like the one I showed you on the previous slide, are on the order of a few parsecs. But GMCs are on the order of a few hundred parsecs. And I think you probably know where I'm going. GMCs care a lot about their galactic environment. They care about things like their position among the spiral arms, about the interstellar pressure. And so we really want to be able to resolve galactic disks, which are on the order of tens of kiloparsecs. And further, we've heard a lot this week about how galaxies care about large-scale structure. So now we have this problem that scales many, many orders of magnitude in the spatial scale. And so cosmological simulations, as of only recently, maybe in the past 1 or 2 years, are maybe the perfect place to study how giant molecular clouds and star clusters interact, or at least an interesting place. And today specifically, I'm going to talk to you about the Latte suite of cosmological zooms. So Anna did a great job introducing these, so I'm going to fly through this part. Latte is a suite of cosmological zooms aimed at specifically studying star formation and the ISM in a full cosmological context. The sample contains 8 Milky Way mass systems and 2 local group pairs, and a collection of them are imaged up here. With high mass resolution between 3,500 and 7,000 solar masses for gas, adaptive spatial resolution, on average in the ISM about 20 parsecs, and 1 megayear temporal resolution, which is really important if you want to study how gas evolves. And again, I'm going to fly through this because Anna introduced it, but to form stars, gas must be self-gravitating, it must be dense, above 1,000 atoms per cc, and it must be molecular. And this is really important if you want to study star cluster formation. You need a high density threshold combined with that self-gravity criteria, combined with high spatial resolution, to really be able to find spatially correlated star clusters in your sample. And as well, we use the FIRE2 model for feedback. So this includes both early and late type stellar feedback, things like core collapse supernova, stellar radiation, and stellar winds, right, which gives you feedback on both the stellar scale and the galaxy scale. So within the Latte sample, I'm going to focus on 3 specific galaxies today. They're Milky Way mass halos, and they're run using the standard FIRE2 physics that I just showed you on the previous slide. These are the 3 galaxies in question. So the first one, M12M, M12I, and M12F. And these 3 images show you gas surface density projections of the 3 disks. Each one is about 40 kpc across. And the reason we choose these 3 galaxies is because, as you can see, their morphology is a little different, but they're all in Milky Way mass halos. So M12M is a nice, quiet, flocculent spiral. It hasn't had an interaction in a really long time. If we go down to M12F, it has had a recent interaction. It's a little more disturbed. So we have a wide-ranging environment that we can look at. If you're so inclined, you can access the data yourself and have a look. So Redshift 0 simulation output for these 3 galaxies and Gaia catalogs generated using Ananke are all available online. So once you do that, you have to actually find giant molecular clouds and star clusters, which is a lot more complicated than it sounds. But the way that we've started to do this is to use a friends of friends algorithm. So basically what that means is you find structures where you're connected to all your particle friends by less than some chosen linking length. And you do lots and lots of tests to make sure that you've chosen the right linking length. So in this case, we're going to go with 20 parsecs. And if you want to speed things up, because you have lots of particles, you can make cuts on density and cuts on temperature. But the algorithm isn't very sensitive to those things. It just really helps with efficiency. And so for these 3 galaxies, now overplotted in pink, are the location of the giant molecular clouds that we find. So you can see that they're located along spiral arms and dense ridges, which is good and interesting. And we form a large number per galaxy. And I also want to stress at this point that while this is interesting in and of itself, this is also a pathfinder to develop a pipeline to use on more and more galaxies in the Latte sample, but also to use on higher resolution zooms, which are coming soon. And then you do the same thing with star clusters. This is an effort being led by Sarah Loebman at UC Davis in a paper coming soon. You do the same thing, use a friends of friends algorithm. You can choose different linking lengths depending on how stringent you want to be about your cluster identification. So she's looked for both complexes and smaller clusters, shown in blue here. And you also require that your stars are less than 3 megayears, so we're looking for young objects. And what we find is that we can find spatially well-correlated objects with small age spread and small melodicity spread, but they are a little fluffier in size than we observe. But we are, of course, catching them when they're a little more relaxed after they've formed. So keep an eye out for Sarah's paper on this coming soon. Once you have your sample, you of course have to make sure that when you compare to observed clouds in the local universe and observed clusters in the local universe, you're sort of in a good space. So we can start by looking at the giant molecular cloud sample. So plotted here is the 1D velocity dispersion inside a cloud as a function of the cloud mass. This dashed line shows you where we, our resolution limit basically, where we trust the internal properties of the objects we find. Now plotted in the background, this green shaded region shows you where the clouds in M51 live. This purple shaded region shows you where Milky Way clouds live. And hidden in the back that you can't really see is NGC 300 in blue. And then M12M, I've plotted as an example, is these gray contours. And what you can see is that we are, of course, probing the upper mass end of that mass spectrum, but our velocity dispersions are in the correct ballpark to agree with local clouds. You can do the same thing with star clusters. So again, this is from Sarah Loebman, and she's looked at the slope of the mass spectrum for clusters as a function of mass. All of these symbols show different objects measured in the Milky Way. These 2 points show you she's done M12M and M12I. And you can see again, while we're on the upper mass end of the spectrum, we do agree quite well with observed local objects. So once you've done that, you've confirmed that your clouds and your clusters are sane, you can do fun things. So you can look at how are clouds destroyed by their stellar clusters. So here I'm showing you a zoom in on 2 individual clouds in the sample. And in one case, you have the cloud forming a single stellar cluster. And in this case, you have a cloud forming multiple stellar clusters. So what you can see, the cloud is this overdense region here. If we look 2 megayears later, something has happened, right? It's a lot more diffuse. It's a little more blown up. And if we look in the multiple cluster case, we can see this a lot more dramatically. You can see that the clusters have blown a hole in the middle of the cloud. It's effectively dead. Its star-forming life is over. And this happens really quickly, in only 2 megayears. And in fact, if I look at the entire sample of clouds associated with clusters, only 18% of those survive longer than 2 megayears, which is really interesting because supernovae only set in after 3 megayears. So that means it appears that earlier forms of stellar feedback are responsible for cloud destruction and shutting down star formation. And this is consistent with work recently by Diederik Krausen and Melanie Chavance, as well as by Catherine Gracia. And this makes sense if you consider the energy budget of a stellar cluster. So this is starburst 99 output of a stellar cluster where luminosity is plotted as a function of age. These lines up here show you radiation. So the orange line specifically is FUV. There's stellar winds and supernovae. And what you can see is that you integrate over the entire lifetime of the cluster, FUV dominates the energy budget. It's a different type of energy, of course, than what supernova would impart, but it dominates regardless. And I'm going to take this opportunity for an interlude to advertise some work that I'm doing with James Wadsley in gasoline, where we've modeled for the first time far ultraviolet heating with radiative transfer in a full isolated galaxy disk. That's a synthetic FUV map image there. And what we want to find out is what happens when you add this self-consistent radiative transfer FUV on top of supernova. So these are two phase diagrams for galaxies here. The first is for only supernova, and the second is for supernova plus FUV. And what you find is that when you add more feedback in the form of FUV, you wind up with more cold gas. And I'd love to talk anyone's ear off about this during coffee break, if they're interested. But for now, I have to get back to giant molecular cloud lifetimes. So the way that we're going to do this is we're going to do it the same way that Claire Dobbs does in 2013. Basically what you do, if you want to get the lifetime, is you find a cloud at an arbitrary time step in black, you follow it forward, you follow it backward, and you declare it born or dead when it's either lost 50% of its original mass, or it's no longer the main mass constituent after a merger or a split. So this is still work in progress, but just to sort of put a number in your head, observational measurements put lifetimes on the order of about 10 megayears. This is a normalized histogram of the GMC lifetime in M12M, M12I, and M12F. And I've stacked many time outputs from the runs, so there are thousands and thousands of clouds represented here. And what you find, you can't see the gray bar, but there's a gray bar here showing you that the peak is around 5 megayears, which is on the short side compared to observational estimates. But we also find that no cloud survives longer than about 15 to 17 megayears. But the picture is a little more complicated than that, because I told you that cloud properties, at least, are a strong function of galactic environment, and that clouds can experience collisions and mergers and all kinds of fun things. So what I've done here now is made a series of violin plots. So a violin plot is basically if you take a histogram of GMC lifetime and flip it on its side. So GMC lifetime is here, and I've binned them based on their position in the galaxy. And then I've further gone and split the sample into clouds that live in isolation and experience no collision, and that's the darker color, and clouds that don't live in isolation and experience either a merger or a split throughout their lifetime. And what you see now is that the picture gets a little more complicated. So first of all, the trend is not the same for clouds that have experienced a collision and clouds that have not. You can see that clouds that live in isolation favor maybe shorter lifetimes, whereas clouds that do experience collisions favor larger lifetimes and as a stronger function of galactocentric radius. And what's also interesting is that if you look in a different galaxy, so this is a quieter galaxy, M12M, remember it was a flocculent spiral, you find that the picture is different again. So the picture isn't consistent between the two, and there's so much variation. So like I said, this is still work in progress, and I think there's a lot of interesting stuff to uncover here about the environmental dependence of GMCs and sort of how star clusters interact with them. And I also want to pitch that cosmological zooms are probably a really good place to look at this, because they present us with a great laboratory, because we can build a statistically diverse sample of galaxies, and we can include all kinds of different physics if that interests you. You can look at how cosmic rays or MHD or rad hydro affect the cluster destruction of clouds. And with that, I will thank you for listening and leave you with my conclusions.
Thank you, Samantha. Do we have any questions for? Go first.
Thank you.
All right.
Hi, Samantha. This is just an algorithm question.
Sure.
So with a fixed linking length
Yeah.
of 20 parsecs, do you have a sort of change in cloud properties as a function of galactocentric distance? And sort of related question, do you know what the Hill radius of your clouds are? Sorry, I'm got
No, I
solar
know.
system on the mind
I know.
here.
Not off the top of my head, I don't know the Hill radius of my clouds, but I can calculate it. So your question was, even with the fixed linking length, is there a change in?
Yeah, typical cloud size?
Yeah, so there is a small change as a function of galactocentric radius with the cloud properties, even with the fixed linking length. But I would like to explore other methods as
Because
well.
I've been
yeah.
thinking about this in terms of protoplanetary disks.
Ah,
So
okay.
we should talk.
We should talk.
Any other questions? All right, I'll go to the back there.
This is spectacular work, Sam.
Thank you.
I was wondering if you've looked at, so Do you know Sarah Jefferson's
I do,
paper on
yes.
the cloud lifetime?
Yes.
So she basically sums up a bunch of cloud destruction rates. Have you
Yes.
looked at like the variation you see? Have you tried to see like, oh, this is because the shear time's getting
know.
big, or this one's
Yeah.
because the
Yeah. So this has literally been in the last week, so it's on my to-do list.
Cool.
Yeah, absolutely.
And we'll take one last question.
So I can't quite remember, but how many resolution elements on average is each cloud and or globular cluster simulation?
So for a star cluster, it would be across. It would be maybe a few resolution elements, and for a cloud, at least 10.
So I guess I'm curious in terms of destruction of both of those things or their evolution. Are you at all worried that let's say you have a massive dark matter particle nearby
Oh.
that could artificially heat it over time that could contribute to
I
destruction?
don't think so. I think we're okay with the dark matter. But
Why?
so Andrew, do you have a comment on dark
The force
matter?
softening is much larger than the size of the typical GMC for the dark matter.
Okay.
So we count if you look at the fire two methods paper, we tried calculating the numerical heating rates from dark matter interactions, and they're pretty negligible on these scales.
All right, let's thank Samantha again. And our next speaker, our last speaker for today is